Well, we have learned that rational numbers are numbers that can be written where both the numerator and denominator are integers in a fraction. That means that if we wanted to prove that something was rational, right here, let's see, I guess I don't even have a pen. Rational, we would have to prove that it can be written as a fraction where the numerator is an integer and the denominator is an integer. Now, I remember distinctly learning these proofs in 7th and 8th grade. I learned it from Mr. Erickson in 7th grade and then had to be refreshed in 8th grade. And when Mr. Imboden went over how it's done again, I went, oh yeah, I remember. And then in 9th grade, when I was in algebra, of course, I already knew it after having 2 years. Now, in the accelerated situation that we have now, the 7th and 8th grade don't do this. They head them right to algebra, and it's very rare that these proofs are taught. In fact, I think I'm the only one that I remember doing this, although I could be wrong. There's certainly got to be some other diehards besides me. Now, a repeating decimal is one that can be written like 0.3 with a little line over it. Or we could have 0.32 with a little line over it. Or let's say 0.345 with the line over it. This would mean that this would say that this number is 33333 going on forever. And this would mean that this is 0.323232 going on forever, and this one would be 0.345345 going on forever and ever. These are repeating decimals. Now the proof is kind of simple. We want to find a number, a mystery number, and we hope it's going to turn out to be a rational number, that is equal to 0.3 repeating. So I'm going to write it this way and then put the repeat over that last digit. Now, what Mr. Erickson said and Mr. Imboden said is that you have to look at your pattern and say, what would you have to multiply this by to move it over one pattern? Well, that would mean to move it over to here. So that would require only a 10x would equal to 3.3333 going on forever. Then draw a line. Since we have two balanced equations, we could subtract them. And so we get that 9x is equal to 3. Solving for x, x is equal to 3/9, or 1/3, which is a fraction. So is this, a fraction made up of integers, thus proving that 0.3 repeating is rational. In fact, we all knew that it was worth 1/3. Let's look at this 0.32. So Mr. Erickson said, put that down, x equals 0.3232. Then ask yourself, what would you have to multiply that by to move it over one pattern? Well, I'd have to multiply it by 100. 100x is equal to 32.32, and both of these are repeating forever and ever. Draw the line and subtract. We get 99x is 32, and x is equal to 32/99. And if you divide that on a calculator, you see you will indeed get that repeating decimal. And because 32 is an integer and 99 is an integer, we have written this number as a fraction made up of integers, so that proves it's rational. Now the 3, 4, 5, let's get rid of some of this stuff so we can put in the 3, 4, 5. Let's say if x, getting the eraser, if x is equal to 0.345345, repeating forever, then what would I have to multiply to move it over one pattern? And that would be 100. x is equal to, no, not 100x, I made a mistake. 1000x is 345.345, going on forever and ever. Subtract, this would be 345, and this would be 999x is equal to that, and x is equal to 345, an integer divided by 999, an integer. Now this is divisible by 3. 4 and 5 is 9, and 3 is 12, and this is divisible by 9. We could reduce this all by 3, but even this proves that it's rational, because those are two integers that are equivalent to our original thing. Now it may occur to some of you that maybe the repeat doesn't start right at the decimal point. Maybe it starts somewhere else. Maybe there's a few digits and then the repeat starts. What would you do then? I hope that you can think about this and maybe figure it out for yourself. I can't remember whether we were showed this or if it was like an extra credit question. What if our x were something like, I'm not using the pen, why am I using the mouse? That's too hard to draw with. What if it were like 123.82343434, and the 34 was the repeating part? What we would have to do, why don't you stop this tape and see if you could figure this out by yourself, and then, or this CD or whatever, this video, see if you could figure out what fraction would prove that this is a rational number since it is a repeating decimal. I hope you took time to try it on your own. I'm going to show you what you do just in case. What you have to do is notice when the pattern starts and then when it starts again. So you have to get the decimal point over to where the pattern starts, because we need to subtract off all the decimal parts. So to move this over, I would have to multiply by 100. So instead of using this x, I'm going to use 100x is equal to 123.82.343434. And then to move it over one more pattern so that I get the 343434, I would have a 34 here and a 2, 8, 3, 2, 1, I guess. 1, 2, 3, 8, 2, 3, 4. See if I copied it wrong. 1, 2, 3, 8, 2, 3, 4, 3, 4. In order to move it over there, I would have to multiply by the 100 that I already multiplied it by, plus 2 more zeros to get it to that. So now I draw my line and subtract my two equations, and I'll get 0, 0. That's those. I'm not lining things up very well. 9,990. 9,900x is equal to, all of this is going to subtract off. That's going to be a 2. 5 and 8 is 13. 8 takes me to 11. 7, 5. 2, 2, 1. And then, that's really messy, Leslie. 9900x is equal to 1225852. And if I'm right, then x would equal to 1225852, if I haven't lost in my bad handwriting. Now, if you don't mind, I'm going to check this on the calculator to see if it gives me that repeating decimal, because, although I don't there's my calculator, because I'm not trusting all of my math here. Looks like I got the right numbers even in the mess of all my handwriting. I'd suggest, if you're doing a proof like this, that you keep your handwriting neater than what I have. But I am writing with a computer and not with a pencil. So, hope you understand these proofs that repeating decimals are rational. To me, it was one of the first times I had to prove things in my mathematical career, and it set the tone for what was to come later. Bye.